Hello. In this lecture of symmetries, particles and fields, we are going to start by finishing off this discussion of the tensor product of representations of the Lie algebra of SU2. And then we're going to move on to relativistic symmetries. And in particular, we're going to start with the Lorentz group. And if we have time, we'll derive the Lie algebra of the Lorentz group. Okay, so if you remember at the end of last lecture, we were setting up the tensor product of two representations, d lambda and d lambda prime, of the Lie algebra of SU2. So the tensor product is, by this theorem that we saw before, is equal to the direct sum of some other representations of the Lie algebra, along with some multiplicities. So these multiplicities are in the natural numbers, including the number 0. So for the individual eigenspaces of d lambda and d lambda primed, we want to specify what they are. So we have eigenvectors of d of h for so we have eigenvectors of d of h, v lambda and v lambda prime. So actually we'll call those with small lambdas. So they're going to call the eigenvalues lambda and lambda prime, and the eigenvectors v lambda and v lambda prime. All right, so our eigenvector, where the value is in this set of minus lambda plus 2 all the way up to lambda. So these are the facts that we know from the properties of representations of Lie algebra of SU2 that we worked out a lecture or two ago. This is property A, I think, capital A. And v prime lambda prime, similarly, is in some set S subscript lambda prime, and it's the same thing, but with a lambda prime replacing the lambda. So each of the eigenvalues differs by 2 units. Okay, so we have that d lambda of h acting on v lambda is lambda, v lambda, that's just the eigenvalue equation. And we have the following one. So now what we want to do is construct a basis for the tensor product. Basis of tensor products of the representation space eigenvectors. So I'm going to call this basis B, and this is the set of all such tensor products of eigenvectors. Such that lambda is in S lambda and lambda prime is in S lambda prime. So these basis vectors are now eigenvectors of the tensor product of the representations. So these basis vectors are eigenvectors of dh cross, d lambda cross d lambda prime as a function of acting on h. So in other words, d lambda cross d lambda prime corresponding to the diagonal generator h, acting on v lambda cross v prime lambda prime is equal to, well, we know, so now we use the general properties of tensor products, the tensor products of representations. And so we get the representation under the first rep acting on the V lambda cross V prime lambda prime plus V lambda with tensor product of D lambda prime of H acting on V prime lambda prime. V prime lambda prime. Okay, so then we just look back to our eigenvalue equations and we see that this is equal to lambda plus lambda prime of V lambda cross V prime lambda prime. So what we've proved here is that the weights add in the tensor product. So in other words, the weights of the tensor product of our representations are in this new space S lambda comma lambda prime, which is the set of all lambda plus lambda primes such that lambda is in S lambda and lambda prime is in S lambda prime. Okay, so property B, capital B of Lie algebras of SU2 was that you know, the states all have multiplicity 1, and in particular the highest weight state has multiplicity 1. And since this tensor product is supposed to be a representation of the Lie algebra itself, then that must also have multiplicity 1. So the highest weight state has multiplicity 1. So what we're going to do is introduce this notation. Well, the highest weight state is when we have the eigenvalues equal to big lambda plus big lambda prime, actually. And we're going to call the rest as d bar. So this d bar means the remainder, basically. So what's in this remainder? Well, again, its multiplicity of states must all be 1. And the highest weight is also multiplicity 1. And of course, the highest weight of the remainder is going to be when we have the previous highest weight minus 2 units. So it's lambda plus lambda prime minus 2. So again, with multiplicity 1. So writing this down, we have d lambda plus lambda prime plus d lambda plus lambda prime minus 2 plus, now I write the remainder of this with 2 bars. Okay, so every time we add an extra remainder, we add an extra bar. And what we do is we iterate this process. To get the final expression for our tensor product of representations, d lambda plus lambda prime plus d lambda plus lambda prime minus 2 plus a bunch of terms plus d lambda minus lambda prime. Now, why have I stopped at d modulus lambda minus lambda prime? Well, we run out of eigenspaces there. And this is to ensure that the dimension of this tensor product of representations, well, we start off with something. So the dimension of this tensor product should be the dimension of the first representation multiplied by the dimension of the second. So it should be lambda plus 1 times lambda prime plus 1, because remember, I think it was property C that we had before was that the dimensionality of the representation is just lambda plus 1. But you can check that this summing up all the terms on this right hand side gives you the same result if we only go down to mod lambda minus lambda prime. For an example, let's check a result that we already know and plug it into this formula. So if we take d1 cross d1, this formula gives us d2 plus d0. And if we turn this back into angular momentum states, then we see that the combination, the tensor product of 2j equals to half states gives us a j equal to 1 state plus a j equal to 0 state. And this agrees with what we know about the addition of angular momentum in quantum states, for instance. So in our alternative notation, where we label the dimensionality of the representation space, so rep space notation, so instead of d1, we have a 2. So this is 2 cross a 2 is equal to 3 plus 1. So remember, because this is how the representation space tensor product works, that it's the representation space both of the group and of the Lie algebra, and so this works for the group and the Lie algebra of the group. Okay, so from this and from our previous discussion about the tensor representation, so we see from this and previous discussion that if we want to obtain the 3 here, so we take the 3 irreducible representation of SU2 or Lie algebra of SU2. Then let's talk about the group just to be clear of the group. We take the symmetric combination of 2 cross 2 and project out the singlet. In other words, we make it traceless. So, okay, let's take, to show you how we do that in the formula, take fundamental SU2 vectors. So we'll take them to be U and V, and they have an index I and J. And all these indices are just either 1 or 2. So they're fundamental indices. And then our ijth component of the 3, UKVL, Okay, and then so the symmetric combination we're going to write in terms of Kronecker deltas, delta Ki, delta Lj plus delta Kj, delta Li divided by 2, minus, and then a half delta KL delta Ij. That projects out the singlet component. Good. So this concludes our discussion of the Lie algebra of SU2. It also finishes this chapter on SO3 and SU2. And we can start on the next chapter, chapter 5. Relativistic symmetries. So there are more than one, so I should say symmetries. Okay. So we saw in the previous chapter that symmetry with respect to three-dimensional rotation, these are important in quantum mechanical, i.e. non-relativistic settings. But in high energy physics, Lorentz transformations are of vital importance because we're getting effects because we become close to the speed of light. So let us discuss the Lorentz group. Okay, so I'm going to want to work with 4 vectors, and space-time. So let's put Greek letters as space-time indices. So the idea here is that 0 is going to be the time coordinate, and the others will be the spatial coordinates. We'll put, sometimes we want to just write down 3 spatial coordinates, and we'll use ordinary Roman letters for those here. So in other words, we can write down our 4 vector x mu. So this is the time component and the set of the xi's, so x1, x2, x3. This is in real numbers to the 4. So each of one of these coordinates is a real number. So let's define the Lorentz group. Many of you will have seen the definition before. So the Lorentz group is the group of transformations where we transform x into x prime mu, which leaves x squared invariant, and I'm going to define x squared to be x mu eta mu nu x nu invariant. So eta mu nu is this so-called flat space time Minkowski metric. Okay, so the idea here is that x prime and x prime and x are related just by a linear transformation. There's some matrix which gets you from x prime to x. So we put this matrix equal to lambda. So lambda mu nu x nu. So remember the convention here is that we write the row indices first and then the column indices. So that for some, this is what we put that for some matrix lambda. Okay, now, so the important thing is that x squared equals x prime squared. Well, this implies that lambda mu rho eta mu nu lambda nu sigma is equal to eta rho sigma. And I'm going to call this equation 5.1. Okay, so we've written it down in terms of components, but let's write it in terms of matrices. So this thing on the left is a matrix product if I just take the transpose of this lambda on the left. So lambda transpose times eta written as a matrix times lambda is equal to eta. And this is 5.2. Now, if you look back to our discussion of pseudo orthogonal groups in chapter 2, this is an equation of one such group. So lambda belongs to the group 0, 1, 3. So we precisely have this metric where there are 3 minus 1s and 1 plus 1. So we're going to define a contravariant 4 vector. That's the kind of vector that we've seen already with an upstairs index. So under the Lorentz transformation, this goes to, just like x mu, it gets a factor of lambda. But we define a covariant for vector we write as u with a mu downstairs now. This goes to u nu prime, u mu prime is equal to u nu lambda to the minus 1. So with a downstairs index, we mean lambda to the minus 1. I think that's mu, yeah. Okay, going back to matrix notation now. If I consider some object V transposed times eta in matrix notation, so V prime transposed is just a row, a 4-dimensional row vector now. And I substitute in for V prime from this equation, then I get V transposed lambda transposed. Okay, now I use 5.2. And I can, from 5.2, given that lambda is invertible, I can multiply on the right, I can act on lambda to the minus 1 with 5.2, and I get V transposed eta lambda to the minus 1. Okay. So what we see is that this object V transposed eta, that transforms with a lambda to the minus 1. So that means that V transposed eta, or in index notation, it's V mu eta mu nu. This is covariant. And we define the inverse of eta with downstairs indices. As eta with upstairs indices. In other words, we have eta mu lambda nu is equal to delta mu nu. So with this in mind, we use eta to raise or lower indices. So we can also raise indices in a way that you're probably familiar with already. And again, the same proof as we just had this one-line proof, essentially the same. But if you have this object eta times u, you can prove that that's contravariant. In other words, it transforms with a lambda. Okay, now This lambda is going to be close to the identity. I'm going to take an infinitesimal Lorentz transformation now. Lambda mu nu is going to be the identity matrix plus some small difference from the identity plus order terms that are second order in this small parameter omega. Okay, and then now I can apply 5.1 to this. In fact, I can plug in, substitute in to 5.1, and this implies that once you've lowered and raised an index, you'll see that omega mu nu is minus omega nu mu. So omega is anti-symmetric under switching the two indices if they're upstairs. It's also, you can prove that this implies it's also anti-symmetric if they're both downstairs. If one's upstairs and one's downstairs, they're not anti-symmetric. You've got to be careful with that. All right, so let's just discuss the structure of the Lorentz group now. Because I've been a bit fast with just assuming lambda is close to the identity. In fact, there are some Lorentz transformations which aren't. And we can look at this equation 5.1. We can take, well, let's take actually 5.2. Let's take the matrix, let's take the determinant of this. So we get determinant of each side. The determinant of products is equal to the product of the determinants, and the transpose doesn't make any difference to the determinant. So what we get here is that det of lambda squared is equal to +1. And so 5.2 implies that the det of lambda is equal to plus or minus 1. And if we multiply out and look at the 0, 0 component of this equation, what you'll see is that lambda 0, 0 squared is 1 plus sum from I equals 1 to 3 of lambda I 0 squared. So whatever lambda is, remember lambda I 0 is real, so this number is bigger than or equal to 1. So what we've proved is that lambda 0, 0 is either bigger than or equal to 1, or it's less than or equal to -1. So we have two options for the sign of the determinant and two options for the sign of the 0, 0th entry. That means it's split into 4 parts. So they're actually disconnected parts. Depending on the determinant and the sign of the 0, 0th component. Okay, so the part actually that we expanded here above, close to the identity, is continuously connected to it, to the identity. So the part connected to the identity E has determinant lambda equal to +1 and lambda 0, 0 is bigger than or equal to 1. This part's called the proper orthogonal Lorentz group. And it's written with an up arrow. So, okay, so because, of course, as soon as we put det equals det lambda is +1, we get a special in front, and it's 0,1,3. But we write this up arrow to denote it's this part continuously connected to the identity. And of course, this is the part we get by exponentiating the Lie algebra. So what about the other bits of the other Lorentz transformations? Well, they can be obtained by multiplying this part. So I'm going to write this as the exponential. Will I write it now? No, I won't write it yet. I'll write it later. So multiplying the exponentiated bit by a matrix T, which is 1 minus 1 minus 1 is minus 1. Oh, sorry. There's a minus in the first component, but not in the others. And or a matrix called P, which is 1 minus 1 minus 1 minus 1. So what T does, of course, is it just reverses the time component. This is time inversion. And P is parity reversal. So here the spatial components go to minus themselves. So let's draw a picture now of the 4 disconnected parts of the Lorentz group. So we have the bit, so we exponentiate the Lie algebra, and we can get this bit with det is +1 and lambda 0, 0 is bigger than or equal to 1. And this is called the proper orthogonal Lorentz group, and it's denoted SO1,3 with an up arrow. But then if we multiply by time, by this T reversal, we can get to, well, we get to det lambda is now -1 and lambda 0, 0 is less than or equal to -1. If we now multiply by parity, we get to det lambda is now +1 and lambda 0, 0 is still negative, less than or equal to -1. And there's one more piece where we get to det lambda is -1 and lambda 0, 0 bigger than or equal to 1. So this is a picture of the Lorentz group. So what we're going to do now is look more carefully into this top left-hand corner, because you know, the rest, we know how to reach the other disconnected parts now with these matrices P and T. Let's now, I'm just going to give you some results on members of the Lorentz group. So actually these come in 2 classes. we can have spatial rotations or reflections. And that's where lambda is of a particular form, which I'm going to call lambda sub r, where we have ones and zeros on the top row and column. But there's a 3 by 3 matrix R in the bottom right-hand block, and R is in O3. So these ones actually form a subgroup of the original group. So if R is in O3, you can convince yourself very quickly that this implies that lambda times lambda transposed is equal to the identity matrix. And to convince yourself it's a subgroup, you need to prove, which is like a one-line proof, that lambda r prime is lambda r prime. And indeed, just by multiplying the matrices in this form, you can see that that's the case. Okay, B, we have Lorentz Boosts. So these ones have a different form. They're described, well, we can describe them by an angle and some fixed axis n. So this is defined to be a 4 by 4 matrix where we have cos theta, sine theta times n transposed. So again, I've split it up into kind of there's a 3 by 3 lower hand block. And here we have sine theta n. And in this bottom 3 by 3 block, we have I3 plus cos theta minus 1 n transposed. This describes a Lorentz transformation with velocity v is n tanh theta. Now, yes, there is an exercise in the book on this. These actually don't form a subgroup because if you do 2 successive Lorentz boosts, you can end up with a rotation which isn't described by the Lorentz boost. So, okay. A Lorentz transformation in general can be written as lambda equal to lambda r lambda b for some r theta and n. Okay, good. So what we want to do now, I mean, those are members of the group itself. We want to look at the Lie algebra. We want to find the Lie algebra actually for the Lorentz group. So, okay, we're gonna be a bit schizophrenic here and sometimes do Lorentz transformation, infinitesimal Lorentz transformations, and sometimes do large ones, but I'll try to be explicit. Take 2 infinitesimal Lorentz transformations. So we have an I subscript suffix, and these are going to be ones close to the identity. where I is in 1 and 2, and we calculate the commutator. So lambda c is defined to be lambda 1, lambda 2, which is lambda 2. If you look at the definition of commutator, it's like this. Oops. Now, it's about three lines of trivial algebra to obtain. So if you substitute in the lambda i's to this and you forget the order, terms of various orders, what you should get is the following. So you should get omega 2 commuted with omega 1. Okay, so what I've done is I've identified the terms of order omega 1, omega 2, but I haven't bothered calculating the terms of omega 1 squared or omega 2 squared. So this additional piece I'm going to define as omega c, or omega mu nu. So this is, if we only had a single Lorentz transformation, I'm going to define, well, I'm just going to put this equal to omega c, okay? Now, what happens is actually that, often we're going to be interested in Lorentz transformations on quantum states. Yes, okay. Let me just say now that, okay, just forgetting the infinitesimal transformations for a moment, I can write some lambda is equal to exponential of, some parameters times some matrices, which are the Lie algebra, right? This is the part connected to the identity. And I'm going to parameterize it in a particular way. It's going to be convenient to parameterize it like this. These are parameters. And M rho sigma are 4x4 matrices. So each one of these, each component of this is a 4x4 matrix. When we go infinitesimal, we use small omega. The M's are going to be the elements of the Lie algebra. For infinitesimal transformations, big omegas are going to go to small omegas, just to remind us that they're infinitesimal. Okay, good. But what happens is, acting on a quantum state, these M rho sigmas are promoted to anti-Hermitian operators that act on the states. To anti-Hermitian operators. And then instead of lambda, we obtain a unitary operator to act on the quantum states. So our unitary operator corresponding to this lambda is then well, it's still x half omega rho sigma m rho sigma. Now, we note that from our previous work, when omega is infinitesimal, we see that it's anti-symmetric in rho and sigma, and that's going to be the same for the larger transformations. And it's then the same for the m's as well. So now, if we expand out this unitary operator in terms of a small, so strictly speaking, this is of a large transformation. So expanding u of lambda of omega, well, this is going to be 1 plus a half omega rho sigma m rho sigma plus dot dot dot. Now, we know that we're going to need that the unitary operator representing the product of two Lorentz transformations, when acting on a quantum state, we're going to need that to follow the following thing. So it's the product of the unitary operators of each Lorentz transformation. And so what I want to do now is calculate the unitary operator corresponding to this commutator here. So all I do is I do some expanding and I get 1 plus 1/2 omega 2 comma omega 1 rho sigma m rho sigma. So this is, remember this is omega c. And remember that because of the previous, this property, this has to be equal to u of lambda 2 to the minus 1, u of lambda 1 to the minus 1, u of lambda 2, u of lambda 1. And this is equal to 1 plus 1/4 omega 2 mu nu m mu nu, comma, omega 1 rho sigma m rho sigma, plus order omega 1 squared, order omega 2 squared. So what we do is we now equate this term and this term. So equating the circled terms. So in other words, the terms, all terms proportional to omega 1, omega 2. Components of omega 1, omega 2. Then we obtain the following. So the idea is, what I want to do here, we're beginning to get something that looks like a Lie algebra. Remember, the M's are supposed to be elements of the Lie algebra, and the Lie algebra usually is written in terms of the commutator of elements, and you get something proportional to an element or to the sum of some elements. And so all we have to do is take into account that these omegas are arbitrary antisymmetric parameters. So we have to take into account that they're antisymmetric, But when you do that, it's 3 lines just to check. And what you want to get the same factors of omega-1 and omega-2 on the left and the right-hand sides of this equation. And this will imply for you that m mu nu m rho sigma is equal to eta rho nu m mu nu minus eta sigma nu m mu rho minus eta mu sigma m rho nu plus eta mu rho m sigma nu. If you want more help on getting between the previous line and this one, just look in the book. I've laid it out in full there. That's good. So we'll stop here. Next time, we'll look at the different components of this, the spatial components, the time components, and so on, derive something else about the Lie algebra of this proper orthogonal Lorentz group. And then we'll look at some of the representation spaces that this acts on, in particular spinors and tensorial representations. And then we'll go to generalize this to add in the fact that you can do translations in space and time, as well as these boosts in terms of velocities. And that leads us to the definition of the Poincare group.